Welcome to Turing Point YouTube channel for combinatorial optimization from a new perspective. We have so far addressed different results on pedigree polytopes. In this episode 7, we define and prove results on pedigree packability. Videos on pedigree polytopes. Presented by Teru Arthur Nari. Proudly sponsored by Whole New World Limited, New Zealand. What is pedigree packability? We have shown nk-1, rk-1, mu is well defined, and assume fk is feasible. Now we like to know whether for any arc L, the arc flow in Fk can come from a set of pedigree flows available in the restricted network for L, namely, nk-1L. If the arc flow can be expressed as the sum of the flows along pedigree paths in the restricted network nk-1L, then we say the arc flow for L is pedigree packable. We can formally define pedigree packability, as given in definition 5.8. Condition A ensures the flow along the pedigrees are non-negative. Condition B ensures the lone sink in NL-1L is E alpha, and so all pedigrees chosen are ending in E alpha. Condition C ensures the capacity restrictions for nodes in NL-1L are not violated. And finally D ensures the tidal flow along chosen pedigrees are equal to the arc flow Vf. Definition 5.9 gives what is meant by an extension of a pedigree pack. Every pedigree in the pack can be extended to a pedigree in pk+1. We are interested in the pedigree packability of any arc flow in Fk. If the arc in Fk connects a rigid pedigree P, then we have a pedigree in pk+1. So we only need to check this for other arcs in Fk that connect to origins in Fk that are not rigid pedigrees. While proving this, we use the fact X is in PMI, N. Theorem 5.2 is the main result of this episode. This theorem asserts that any flow along an arc L in Fk is pedigree packable. And for any given E', we can have feasible flows along arcs L such that the net requirement at E' is satisfied, that is, after subtracting the total flow from rigid pedigree nodes in Fk, namely, delta prime. Finally, the pedigree pack consists of all pedigrees, X super R, active for a lambda in capital lambda K of X, such that xkr of E equals 1 and E' has a generator in the pedigree X super R. We make a few observations. First, X given k+1 is in the polytope PMI, k+1. Second, X given K is in convex PK, the pedigree polytope for K implies, for all lambda in capital lambda K, X given K, can be written as a convex combination of pedigrees, XR4R, in I suffix lambda. Recall the MI formulation for K. The slack variable vector corresponding to a K-tour for pedigree, X, R, be denoted by U, super, R. Similarly, let U, super, K, denote the slack variable vector, for X given K. Then, we can write U super, K, as the sum over R in I suffix lambda, of the products, lambda R, times, U, super, R. We show observation 3, from the previous slide, as follows. Recall lemma 3.1 from chapter 3 of Pedigree polytopes. For every pedigree for K, there is an integer solution to the MI formulation, and the corresponding slack variable vector is the incident vector of the tour, which is in one-to-one correspondence with the pedigree. We denote this by U, super, R. Remember that U super, K, is the slack variable vector corresponding to X given K. So, xk plus 1, E, is less than or equal to U super, K, E. Now, xk plus 1, E, is positive, and so U super, K, E, is positive as well. Applying lemma 3.1, for K and noticing X given K, is in the pedigree polytope for K, convex pk. Consider any weight vector lambda, in capital lambda K, X. We find the same lambda can be used to write U super, K, the slack variable vector for X given K, as a convex combination of U super R, for R in lambda, where U super R is the slack variable vector corresponding to XR. We need some notation here. Let the set of all pedigrees ending in E be denoted by I suffix E, a subset of I lambda. We have lambda saturates the node capacity, Cu, for any node, U in the network nk-1. Let J suffix E prime denote the subset of pedigrees that have a generator of E prime. Now we can write U super, K, E prime equals sum over R in I lambda intersection J suffix E prime, of product lambda I U super R.
The proof of theorem 5.2 follows easily from the observations we have made so far. One important corollary of this theorem, it is used later, and is given X belong to PMIN and XK, X given K, belonging to convex PK, if xk plus 1 E prime equal to 1 for some E prime, then X given K plus 1 belongs to convex PK plus 1. Of course, this corollary can be proved directly also, and this has been done in a recent article uploaded on arXiv. Even though we can apply pedigree packability for any E prime with X K plus 1 E prime positive, the simultaneous application of this theorem for more than one E prime in general may not be correct. We shall see example 5.4 from Pedigree polytope next. Is from the book, chapter 5, example 5.4. Here, n equal to 6, and we have shown in the diagram the nodes that have positive capacities. First, we consider F4 and we find F4 is feasible and there are no rigid arcs. So N4 is same as F4 and we proceed to build F5. F5 is built by considering different arcs like 512 to 613 and looking at the restricted network corresponding to that. And here the restricted network consists of 4, 2, 3 and 512 with capacity 14. So that becomes the, of course we can have a flow of 14 unit. So that goes to 512. So that becomes the capacity for this arc. Similarly, we can do for arc 512623, and in this case the restricted network has only 413 and 512 connected by the arc and having capacity 3/4. And so we have a flow of 1/2 unit coming to 512. So that becomes the capacity for this arc and so on. So we find the capacity for 624, etc. In this way, we can complete the Fy network and check that F5 is feasible. And Fy has no rigid arcs. The question is, does X belong to convex pk? Notice that each of the nodes 6ij for corresponding to triangle ij6 are individually pedigree packable. That means we do have pedigrees that can bring the required node capacity at 613, 623, etc., 624 individually through pedigree paths. But collectively, can we do that? That's what the question, does X belong to convex pk? And we can check that X does not belong to convex pk. You can check why it fails. It fails because some of the node capacities are violated when you simultaneously try to have pedigree flows. For instance, 624 can have a flow of 14 unit from 423. But once we have that, we cannot have 613 have a flow of 14 from 423 because that capacity, node capacity, has been saturated already. So with this, we conclude this episode, and in the next episode, we will be considering the multi-commodity flow problem, which will be used to check whether the necessary and sufficient conditions are satisfied by the network or not. Thank you.